All right, everyone, welcome back. Our next speaker today is Professor Leon Simon from Stanford University. Professor Simon is also a recipient of the Frontiers of Science Reward, and he'll present to you singularities of minimal submanifolds. Let's welcome Professor Simon.
Thank you very much, and thanks for the invitation to speak at this nice conference. Okay, so let's start. I want to start with the most general notion of an n-dimensional minimal submanifold, which is just something that can basically have a very large singular set. That is, it's M is simply a closed rectifiable set, and there's an upper semi-continuous density function defined on that closed rectifiable set. And the area then is just the integral, where d mu is the density times Hausdorff, n-dimensional Hausdorff measure. And the regular set is the set of points such that the rectifiable set intersect B rho, centered at X, is a smooth embedded hypersurface for some rho bigger than 0. Notice by definition that's a relatively open subset of M. And the singular set is what's left. That's, of course, a closed subset there, the complement of the regular set. In this setting, almost nothing is known. It's really a slight embarrassment for the people working in this field. The only real thing known about the singular set in this general setting is that the singular set is nowhere dense. That's pretty pathetic, right? The other general thing you can say about singularities in any setting, including this general setting, is that they always look conical. These are consequences of the monotonicity formula. And that simply means that at every sufficiently small scale, if you blow up by a factor rho to, first of all, you translate the point you're interested in to the origin. And then you blow up by a factor rho to the -1. Rho is a very small number. So we're translating the point we're interested in to the origin and then blowing everything up by a large factor. When you do that, you'll always see a cone, a minimal cone there that this is close to. But the intriguing thing is that it is not known if that cone's unique. It may change as rho changes. So even though you're always close to a cone, that cone may be varying. There may be a whole one-parameter family of cones that change as you approach that. So in this general setting, it's the situation is not very satisfactory. Almost nothing known, but fortunately, the situation is much better for special classes of minimal submanifolds. In particular, if you look at minimizing M, that is M that minimize area relative to comparisons having the same boundary. In that case, you've got the foundational work of DiGiorgi, James Simons, and Federer. And codimension 1 minimizers, for example, have no singularities at all up to dimension 6, including up to dimension 7, up to dimension 6. No singularities at all. Then at dimension 7, you can have a discrete set of singular points. And for n bigger than or equal to 8, you have a singular set of dimension, Hausdorff dimension, less than or equal to n minus 7. So the singular set is actually at least codimension 7 in the set M. And also in codimension 2 with arbitrary codimension bigger than or equal to 2, arbitrary codimension, there's a result of Federer showing that the singular set of mod 2 minimizers is nicely controlled. Mod 2 minimizer means that you're minimizing area relative to both oriented and unoriented comparisons. And in that case, the dimension of the singular set is less than or equal to n minus 2. And again, it's discrete when n is equal to 2. I should have mentioned, since my colleague and co-author is here, that Rick Schoen and I extended the codimension 1 result to stable minimal submanifolds in 1981. That turned out to be somewhat important because Pitt's minimax procedure requires that you have estimates for stable rather than minimizing. So those existence theorems of Pitt's and require that result. All right. So so as I said, things are much more satisfactory in this case, and I was able to show in 1995 that in all these cases here, the singular set is actually rectifiable in the appropriate dimension. So in the case of hypersurfaces, it's n-7 dimensional rectifiable set. And then the most recent developments concern the case of codimension bigger than or equal to 2 and minimizing, oriented minimizers with codimension bigger than or equal to 2. The regularity theory for that class is much harder than the mod 2 minimizers because of branching. And Almgren was able to prove back in the 1980s that the singular set has dimension less than or equal to n-2 in that case also. And Delelis and Spadaro simplified Almgren's method somewhat and shortened it in their papers 2013-14. So that's rather satisfactory now. And then most recently, most recently, let's not get too carried away here. Most recently, Krummel and Ramasekara and Delelis, Minter and Skorobakova. Someone help me out here. Skorobakova, right. Proved that the singular set is n-2 rectifiable. So that's great. So all of these classes have rectifiable sets in the appropriate dimension now. That's known. So they all look like this in this schematic picture. There's always a countable union of C1 manifolds, and the singular set, except up to a set of measure 0, always lies in the union of there's a part of K in each one of these C1 submanifolds. So you get a nice schematic picture like that. But then you see the question is, how bad can that be? Even though it's in a C1 submanifold, that doesn't mean it's a nice looking set. It could be fractional dimensional, for example. So we really wanted to know that. And it turns out that indeed it can be fractional dimensional. So I proved this theorem a couple of years back, that in fact, in high dimensions, high enough dimensions, that is in the dimensions where the minimizing hypersurfaces have singularities, you can take an arbitrary K contained in the Euclidean space RL, L is bigger than or equal to 1 here, and you can find a metric on Rn plus 1 plus L such that that metric is very close to the identity metric, arbitrarily close to the identity metric, and such that there is a smooth, embedded, stable, minimal hypersurface, which has singular set equal to 0 times Rk. So indeed, the singular set can be fractional dimension. In fact, it can be an arbitrary closed subset of RL, which is maybe was not necessarily expected, though people's opinions would have differed on that. So let's make a couple of remarks on that. It's still very open whether or not this phenomenon can happen with respect to real analytic metrics rather than smooth metrics. And my theory has always been that it can't happen with respect to real analytic metrics. And there's recent work of Zekel Yehidi, who showed that indeed, if you've got an analytic metric, and this sort of singularity cannot occur, provided you assume sufficient symmetry of the minimal submanifold. So it's still very much an open question, but at least there's some evidence to support the fact that in the real analytic case, you cannot have this sort of phenomenon. All right. And then another recent result is in lower dimensions, but in codimension at least 3, Senhua Liu in Princeton, using calibration methods, showed that there are examples, again, of minimizers, which have fractional dimensional singular sets. The picture of Liu's example is like this. I hope you can... I hope I can get across what this really is supposed to be depicting. What this is supposed to be depicting is that you've got two smooth minimal submanifolds here, no singularities, and they actually touch along a lower dimensional set. That's the set K. That's the singular set. And he proved he could do this in various dimensions. In fact, all the Almgren strata can be accounted for by this sort of construction. So you get singular set equals just the intersection of two regular minimal submanifolds. And with respect to a suitable C infinity metric, the whole configuration is minimizing. So that's a nice result. Of course, you'll see, as you can see, there's still a huge number of questions that are open in this field. All right, so I want to outline the construction of the main, that required to prove the main theorem now. So I'm only going to outline it in the case L equals 1 because the argument for general lather is basically identical with just notational changes. So here we have K. So the idea is that we start off with the famous James-Simons cone. That's the cone in Rm plus 1, Euclidean, in Rm plus 1 times Rm plus 1, where mod eta equals mod xi, famous James-Simons cone. And m bigger than or equal to 3, of course, because we need the thing be minimizing. And of course, you don't get, there are no such singular cones in dimension less than 7. So this is for an m is equal to 3, this is a 7-dimensional cone sitting in R8 with an isolated singularity at the origin. So you start off with that James-Simons cone, and you prescribe so here's the singular set of the, so then you take the cylinder. You take the Cartesian product of that James-Simons cone with R, and then you take, so that has singularities, of course, along the y-axis. Every point on the y-axis is a singular point because it's the vertex of one of the cross-sectional Simons cones. So you've got that singular set, which is the real line, the y-axis, and then you simply take an arbitrary closed set here. So I've written this as though it's rather simple. So I've got K, such that the complement of K has only got 3 open intervals, but of course, in general, it can be a countable number of open intervals for the complement. And so we start off with that, and then we want to get rid of the singularities in the blue bits. I want to leave the singularities at K, and I want to remove the singularities from the blue parts of the y-axis. So how do we do that? Well, we do that by sewing in smooth surfaces which meet C cross R in a C infinity fashion. Now, of course, that's, I mean, you can always do that, but there's no guarantee that then you're going to be able to find a metric such that this new configuration is still a minimal submanifold, right? So that's the point. So there's severe restrictions on how you can do this sewing so that you can then get a metric. So I want to explain that. So by the way, you should keep in mind that this picture here is a schematic picture in 3 dimensions, but you get the real picture by making an m-fold rotation about the y-axis. So this is actually a very good representation of the real picture. Okay, now, as I said, to get the real picture, you do have to make an m-fold rotation about the y-axis. So that means you're also making an m-fold rotation of these curved bits too. So in the original picture, everything is graphical. You can write this new surface, including the curved bits, as the graph of a function. But in order to get the real picture, you taking account of the m-fold rotation, you have to take the symmetric graph. The symmetric graph is the ordinary graph is just a set of xi, zy, such that z equals u xi y, the usual thing. But in order to get these m-fold rotations into play, you've got to take the set of xi eta y, such that mod eta equals u xi y. So that's what we'll be looking at. We'll be looking at symmetric graphs rather than graphs. But that's about as simple as you could possibly expect if you're trying to construct a complicated singular set. So somehow this is still a fairly simple picture. So let's look at these symmetric graphs. Well, we want to talk about such symmetric graphs being minimal. So that means we should look at the area function of symmetric graphs rather than the area function of the usual graph. And the area functional of the symmetric graph is this thing here. It looks, it's got a part that looks like the functional that you use to get the area of an ordinary graph, except that it's got this factor u to the m, in which is because which comes up because you're taking an m-fold rotation. All right, so that's the area functional, and we want to get take the Euler-Lagrange equation of that area functional and set it equal to 0. We want the new configuration, including the curved bits, to be minimal. So we need to compute the Euler-Lagrange equation, and let's do that. Well, when you compute that Euler-Lagrange equation, it's just a few lines of calculation, completely standard calculation. You find that that you get this, the Euler-Lagrange equation is mu equals 0, where m is this operator. And notice it looks very much like the ordinary mean curvature operator. This bit here looks very much like the ordinary mean curvature operator, but it's got this extra singular bit m over u, and that's a bit threatening because as u here u is positive, but it can be close to 0, so we have to be rather careful about that. So, we want, as I said, we want to solve this equation. Now, of course, we would like to get u to satisfy this equation on the whole region. So let's work out, let's go back for just a second to these curved bits. Notice these curved bits are defined over cusp-like domains. And let's take a closer look at those cusp-like domains here. Here's one connected component of one of those cusp-like domains. It's in the mod xi y plane. And notice I've broken it up into 3 regions. I've taken an arbitrary C infinity function, which vanishes to high order as you approach the singular set. And then I've broken the domain into 2 bits. It's got an inner region where mod xi is less than a half hy over less than a half hy. And the whole domain is the set of points where xi is less than hy. And notice then you've got this sort of transition region. That's this collar type, cusp-like collar region. Now keep in mind that these cusps actually close very sharply because h vanishes to infinite order as you approach the singular part. So, so that's the domain we're going to be looking at in order to solve this this equation. By the way, this equation is called the symmetric minimal surface equation, SME. I'll keep referring to that as SME for the rest of the talk. Okay, so that's our aim, to solve the equation on a domain like this. Now, if we use the whole domain where xi is less than hy, that's this domain here, the entire domain, then of course we can't expect U to join smoothly to the Simon's cone, the Simon's cylinder rather, because that would contradict unique continuation. So we have to be content with the fact that as an initial step, yes, we are going to solve the symmetric minimal surface equation on this domain, but we're not going to get a C infinity join to the original cylinder straight off. So we're going to have to do some extra work after we've solved the equation. But anyway, let's talk about solving the equation. Preliminary to that, let me mention a family of solutions of the symmetric minimal surface equation with just one variable, the radial variable. Then the symmetric minimal surface equation becomes an ODE rather than a PDE. And the actual equation is phi double prime over 1 plus phi prime squared plus m minus m over r, m over mod xi, phi equals m over phi. That's the equation. It's an ODE, a second order ODE. And Bob Hart in 1981 proved that, in fact, on one side of Simon's cone, you do have hypersurfaces which are described by solutions like this. In the special, we actually did it in a general setting, but in the special case of the Simon's cone, you get, you can make a very precise description of what this hypersurface. So the schematic picture is, this is the Simon's cone, C0, and then this is the graph of U. So this is mod xi equals phi of mod xi. Oh, sorry, mod eta equals phi of mod xi. So this picture solution. We're going to make use of these in the rest of the talk in our construction of our solution U. So, so here's the picture that I just tried to sketch on the previous slide. So here we've got the Simon's cylinder, the Simon's cone rather. That's mod eta equals mod xi. And then we've got the Hart-Simon surface, which is mod eta equals this function phi times mod xi. But then you can do rescalings, geometric rescalings. You can do phi tor equals, you can do a rescaling, phi tor equals tor phi r over tor. That's a rescaling by a factor of r, and that gives you a whole foliation, a one parameter family, which gives you a foliation of the whole region mod eta bigger than mod xi. So you foliate the entire region with these rescalings. And one nice fact about these the symmetric graphs of these phis is that they're strictly stable, because the Simon's cone is strictly stable and strictly minimizing, and it turns out that means that these the symmetric graphs of these functions phi and their rescalings, phi sub tor, they are all strictly stable hypersurfaces. That's going to play a very important role here. So in other words, there's a fixed lambda bigger than 0, such that the first eigenvalue of the linearization of the symmetric minimal surface operator at phi is bigger than or equal to lambda, or at phi tor more generally is bigger than or equal to lambda. So that's a very useful fact, and we're going to make use of that. So let's go back to our discussion of actually finding out, actually solving this equation on these cusp-like domains. So let's talk about that. Right. Yeah. Okay. So the construction is going to be, you remember I said that you've got to be very careful about how you construct the curved bits, which are going to be the graph, basically the graph of this solution, at least away from the collar region that I drew in the previous slide. But it turns out you really need to make sure that everything's decaying very rapidly as you approach the cusp points in this region. So, in other words, as you approach these points here, you want to make sure that the solutions you were constructing decay very rapidly as you approach those points. Otherwise, we won't be able to make everything smooth in the final discussion. So let's go back. So in other words, this is what we want. It sounds like a tall order. We want to show that that U approaches the Simon's cone. Notice the Simon's cone is just mod eta equals R, where R is mod xi. So we're looking at the difference, U minus R. That tells you that's the difference between what we're constructing, the solution U, and the Simon's cone. And we want that to be bounded above by an arbitrarily large power of H, which is our given C infinity function. So that sounds like a tall order. And I'm sure the PDE people in the audience realize that if you want to do something like that, then of course what you need are barrier functions which decay at that sort of rate. So that's what you need to do. You need to construct barrier functions which have this sort of decay. So that's the next ingredient here. So as a first step to that, it turns out that you can actually perturb the thing that Bob Hart and I constructed. You can perturb this phi to give a new phi tilde, which is a strict super solution of the symmetric minimal surface operator. So in other words, m phi tilde is not only less than 0, but it's actually less than a small constant times the second derivative. Second derivative is positive because these phi and phi tilde are actually convex, strictly convex functions. All right, so so that's a starting point. But then, so you've got to work out how you're going to get this barrier in the general case, and that's this here. This is the idea. Sort of a nice idea. You look for your barrier function, which is basically a rescaling depending on y of the phi tilde. So this is using that. It's like if we were using phi instead of phi tilde here, this would say that each y equals constant slice of our barrier looks like one of those members of the foliation, one of those phi tors. So that's a very specific form for the possible barrier function. And well, then that turns out to be very fortunate because you just then plug in this, you compute all the derivatives. It's very easy to compute the derivatives of this function directly in terms of the derivatives of phi. And then you use this fact about phi tilde and you make just a few lines of calculation. And then you find that indeed this guy here will be a barrier provided you choose C appropriately. And there are many choices of C. A good one is this. You can take an arbitrary epsilon positive. Taking a positive epsilon is merely a technical step. We're going to let epsilon tend to 0 before we do anything else. But epsilon plus small multiple of negative exponential of beta over h to the alpha, where h again is our given C infinity function, which vanishes on k and C infinity on the whole space. So that's really nice, because notice that does give you, so that does then give you a super solution, but more importantly, you can check very directly that actually the difference between this V epsilon that we've constructed here and phi epsilon r. Now, phi epsilon r is the leaf of the foliation. By the way, there's a misprint here. Everything's supposed to be tilde here. So you can think of it as being phi. It looks very similar to phi, but it's a slight perturbation of phi. So that decays exponentially because of our choice here of the barrier function, which is decaying very rapidly as h tends to 0. So we do get very nice barriers, and that leaves open the possibility that you'll succeed here in your construction. So then we go back to the equation, and we look. Our problem now is to solve the equation, the symmetric minimal surface equation, and we've got to decide which boundary data we're going to use. Well, the idea is to use to try to get a solution try to get a solution. A solution is going to be involving two parameters, t and epsilon, and I'm going to take a two-parameter family of boundary data. Vt epsilon, this is on the boundary of the cusp region. I'm going to take Vt epsilon equals our phi epsilon, and again, there's a misprint there. That's supposed to be phi tilde, plus t times our barrier function. And then you want to use the famous method of continuity. So that's a very simple method. You simply observe that you can trivially solve the symmetric minimal surface equation with this data for t equals 0, because when t equals 0, the boundary data is just phi epsilon, and phi epsilon itself is a solution of the symmetric minimal surface equation. So there's no problem about solving that when t equals 0. And then, of course, by the implicit function theorem, because phi epsilon, because the symmetric graph of phi epsilon is stable, in particular, that means that there is no zero eigenvalue. In fact, all the eigenvalues of the linearized operator are positive. So the implicit function theorem does apply. Remember, to use the implicit function theorem, you need to know that the linearized operator does not have a zero eigenvalue. So we can use that for small t. And then you try to go as far as you can. This is the method of continuity. You define t0 to be sup of a set of Tor such that you can solve right up to Tor for all t up to Tor. And then by taking a priori estimates, elliptic estimates, you can actually pass to the limit and argue that there is a solution at t0 anyway. So you can pass to the limit as t tends to 0. So the main problem now is that t0, this sup may be less than 1. We may not be able to get up to t equals 1. So we have to discuss whether we can do that or not. And what could possibly go wrong? Well, a couple of things can go wrong depending on which class of functions you're working in. Here I'm going to be working in the class of functions which have small y derivative. So that's going to be our class of functions. Notice that's no problem for the initial step that I described, because the particular solution at t equals 0 is phi epsilon of mod psi. It's independent of y. So certainly our solution starts out to have small y derivative, and we build that into the class of functions. And we also need, as I mentioned, that the first eigenvalue, that we don't suddenly hit or not suddenly, that we don't gradually approach a value at t0 where the first eigenvalue of the linearized operator is 0. So we have to worry about that. But anyway, at t0, you have that. and provided we can get around those two difficulties, which I'll come back to in a minute, then the process does work and you can get up to t = 1. So let's assume we don't run into the difficulties. The two possible difficulties are that we run into at t0 we get a value where at t0 we get dyu equals delta. That would be one possible bad development because we need to be working in the class strict inequality. That would be one bad development. And then the other bad possibility is the zero eigenvalue thing. So let's assume that we've got those under control. I'll come back to those. And then you can take the limit as t tends to 1. You can take the limit, rather, as epsilon tends to 0. So we get rid of this parameter, epsilon. That was just for technical reasons that we had that, to make sure we were starting off in a non-degenerate situation. So we then let epsilon tend to 0. And that would give us, as required, a solution to the symmetric minimal surface equation. That's the SME there. And with these nice decay properties, that the order of decay, at least in the collar regions, that's where you get the best value out of these barriers that I constructed. You can check using the barrier functions that I mentioned earlier that you actually get this sort of decay in these collar regions where R is between a half HY and HY. So we would succeed, but as I said, that's the proviso is that we can avoid those two bad developments that I mentioned. So let's talk about those. Right. Yes.
So at this moment, did you change the metric background matching?
No, you see, this is all, for the moment, I haven't even mentioned a metric yet. At the moment, we're just constructing the curved pieces. There's no discussion of metric yet. It's in Euclidean space, yeah. Everything's Euclidean at this stage, yeah. But then I come back to the point that I made earlier. You want your construction of the curved pieces to join smoothly onto the Simon's cylinder. So in order to do that, we make a transition in the transition region where R is between a half HY and HY, and we just plug in, take a convex combination. Take a convex combination between the exact solution and R minus HY. So this is a convex combination between U10, that's the solution you get when you let epsilon tend to 0, and the Simon's cone. The Simon's cone is given by R in this setting. So that's the idea. And notice this works rather nicely because in the transition region, when you differentiate this in the collar, in that transition region, those sort of collar type cusp regions, you have to differentiate this thing R over H, which is very bad. You pick up factor 1 over H every time you differentiate that. But remember, these guys here, these guys are decaying faster than any power of H. That's why we needed to build that into the construction. So this behaves beautifully, smoothly, so it gives you a smooth transition. So let's summarize what we have now. We now let, so from now on we're taking U to be this function, which is a convex combination between the Simon's cone and the solution U10 that we constructed. And what properties does it have? Well, it satisfies the symmetric minimal surface equation in the inner region, no longer in the collar region. And it's got these nice decay properties in the collar region. So that's good. So that's the construction. But I haven't yet explained how we avoided those two bad possibilities, that the eigenvalue might get to 0 at t0 or mod du might be equal to delta t0. Both of those possibilities are eliminated by this Liouville type theorem from a couple of years back. And the Liouville type theorem says that if you've got a solution of the symmetric minimal surface equation on one side of the Simons cylinder, lying on, that's what our thing is. All the constructions we've made in those curved bits do lie on one side of the Simons cylinder. Then indeed, the only possibility is that it itself is a cylinder just given by one of these phi tors, one of the rescalings of phi tor. So that's very nice. And this theorem eliminates both those bad possibilities. I won't give the details of that part of the argument, but both bad possibilities are eliminated by this. I think you can see that by a rescale, if you sort of go back to these properties here, and if you're worried about a point where du might be getting close to delta, you can just rescale. Geometric rescaling doesn't change the y derivative, it leaves it invariant, so we'd still be close to delta. But then if you rescale at a point close to r equals 0, you'll see a picture that looks almost like this. At least as you let the point approach the origin, it actually becomes exactly like this. So then that would be a contradiction, because you'd have a point, something very C2, very close to one of these guys, which has a fairly large y derivative. That can't happen. So there's actually a gap in how big the y derivatives can be for these solutions here. There's a certain delta so that the y derivatives will be less than delta over 2 and never get up to delta. So both the bad possibilities are taken care of by the Liouville type theorem. Yes. Oh, okay, great, thanks. All right, so that's the main step of the argument. Now let's talk about the construction of the metric. So this is a sort of a cheat, you see. I told you there was a metric such that there is then a minimal hypersurface, which is minimal with respect to that metric. What I've done here is actually construct the minimal hypersurface first. Now I'm going to construct the metric to make that into a minimal hypersurface with respect to that metric. And the kind of metric you take is this guy. It looks like the Euclidean metric with respect to the xi and y variables. And it's got this factor it's got this smooth function depending on the xi and y variables in front of the eta parts of the metric. And of course, f has to be smooth everywhere. And I want to construct f so that it's actually close to 1. So that it really is close to the Euclidean metric. So we want to check now that the construction we've made of that original picture, maybe here, yeah. I have to show now that this picture is minimal with respect to that metric. Well, in order to do that, I've got to compute the area functional with respect to that ambient metric and check that this is a stationary point of that. So let's go to that. So here's the area functional. It's a simple computation. You've got to use the area formula to compute the area functional. And you see this. And then you compute the Euler-Lagrange equation. That's, if we can show the Euler-Lagrange equation is 0, then we're finished. That means it is indeed a minimal hypersurface. Well, here's the Euler-Lagrange equation. And very fortunate development, because if you stare at this Euler-Lagrange equation, what you see is here we've got a first order PDE for the metric. And this stuff is all nicely smooth. Remember, u is now fixed, so it's a nice smooth function. U is fixed, completely smooth, so that this has the form. You can write it in this form, du.df. It's better to write everything in terms of 1 minus f rather than f. Then we want f to be close to, then we want f bar to be close to 0 rather than f close, which is the same as f close to 1. And you can rewrite the equation as a nice thing. In fact, here it is here. After a little manipulation, you get a rather nice looking equation. You get, in fact, since I'm a bit short of time, let me skip that detail and let's go back down to this final version. Turns out that what you get, that this thing here actually, in using our infinite decay properties for U, you can actually write this first order PDE for F bar in this way. It's a nice non-degenerate first order PDE with nice right-hand side, very explicit, plus some error terms which are decaying rapidly, infinite order decay. So in fact, you can actually check then using the classical solution method for first order PDEs that indeed there is a solution and it decays to infinite order. And in fact, we end up with a solution which is identically 1 in the inner part of the cusp domains, and F tends to 1 rapidly, decays to this very high order as you approach the K cross R, M plus 1, and F identically 1 in K cross R, plus 1. So that's it. We are finished. Thank you.
Thank you, Professor Simon. Any questions?
Thanks for your nice talk. So is it possible to change the local model from the Simon's cone to other area minimizing?
Yeah, I think that's probably possible. In the paper, I did it for R, for the Simon's cone with 2 parameters, M and N. So Sn cross Sm. That goes through the same way without change. But then if you want to use more general cones, they would have to be strictly stable and strictly minimizing, but all the cones in Lawson's list have that property. So you could use those, but then you would have to work more intrinsically. You could no longer use the symmetric minimal surface equation, which is a tremendous simplification in working in this setting. Yeah.
Other questions?
Excuse me, do you think this kind of construction can be adapted also to other problems in GMT, like harmonic maps or something like that?
Yeah, I haven't really thought about that. That's entirely possible, presumably. Yeah, I think someone should look at that. Yes, definitely. Typically, that might turn out to be harder because working with minimal submanifolds, things are more intrinsic and somehow work out more naturally geometrically. But I don't see any reason why there shouldn't be some way of making construction. I guess the analog of the Simon's cone would be just the map into the sphere or something, right? And you could try a similar technique. Yeah.
Other questions?
Oh, another one.
Is it possible to get some area minimizing hypersurfaces?
Well, these might be area minimizing. We don't know. And they're very explicitly constructed, so there is a chance if one expends enough energy on that, you can actually prove that they're area minimizing. Yeah. I don't guarantee it, however. Yeah.
Other questions? Okay, so if no more questions, let's thank Professor Simon again. We'll have a short break and restart in about 10 minutes.
I think I spotted the typo.